All right. All right, everybody, so we're going to get started. The format for today's recitation is going to be a little bit different from normal. So we're going to talk about embeddings for a little bit, probably around a half hour, maybe a little bit more. And then we're going to do some diving into the baseline implementations for the different homeworks that we've talked about, that we've had so far. For the purposes of embeddings, we're not going to be doing a notebook or something like that. We're just going to be talking about the main ideas behind everything. And then after that, we'll talk about the code for the homeworks. So for the purposes of this presentation, there are two main embedding approaches that we're going to talk about. The first one is Word2Vec, which is probably the more talked about, and then Glove. There are two different approaches of trying to get the same idea, or trying to get at the same idea. And there's a bunch of other implementations and work that happened both before and after these two, we'll call them models, these two models. But these are just the two that we're going to talk about. So the motivation for this is when you're doing machine learning, you can do one-hot vectors of any kind of data. So in this case, we've got a one-hot encoding of the word A and the word abbreviations, and you do it alphabetically until you get to the end of your dictionary. And that's one way of representing your data. So generating a feature vector of the length of your vocabulary, and then whenever you want to represent a word, be it in a time series or in a unigram, some sentence, you could do it like this. So just put a 1 wherever there's a word and put a 0 wherever there isn't a word. And this is called one-hot encoding because there's one value which is hot. There are a couple of obvious problems with this. The biggest one is that words that are very close in meaning and words that are very far apart in meaning have the exact same distance between each other. One along the axis of that vocabulary term. So if you've got the word shoe and loafer, they're going to have the exact same distance as shoe and zebra, even though they're very semantically similar or disparate, depending on the two. And so there have been a bunch of different approaches to try and get at trying to construct feature vectors so that the words or the objects that you're trying to generate a representation for are near to each other even when they're not, and far apart when they're not. So Word2Vec, people tend to think that it's just a method for doing math on top of your words. So you can do king minus man plus woman equals queen, and you can, by doing some sort of vector math on top of your embeddings, you can get vectors that are close to this. And so this does really well on things like analogy data sets and problems. But this wasn't the main contribution when it initially came out. This was kind of an afterthought. And so it's important, but that's not really why Word2Vec was important. So Word2Vec initially was two things. It was a model, or two models, and a training paradigm, we'll call it. If you go and look at the Word2Vec paper, this thing, which is kind of everybody talks about, is really sort of, it's not a footnote, but it's like a single sentence in a second paper after Word2Vec had already been released. So if you go looking for this, it'll be hard to find, but this is what the original paper is for. And this is kind of why it stuck around, because they found a way to generate these kinds of vectors in a fast way, whereas other methods could get at them in some way, but it was really hard to actually generate those vectors computationally. So the two models, there are two models that Word2Vec uses. One is the SIBO, or continuous bag of words. And the reason why it's called the continuous bag of words is because everything is treated as a bag of words. So you've got a one-hot encoding here, and you've got a one-hot encoding on the output. So given the one-hot encoding of word at t+2, t+1, and within some window along your word, predict the word in the middle. And that's for SIBO. And then for skipgram, you do the same thing, only generating from the word that you know, try and predict the surrounding words. This diagram is the one from the paper. It's a little bit confusing because it skips out on a lot of math. This is the one that actually kind of talks about everything. So the way that it works is you've got, let's say that you've got 4 different words in your context and 5 words in total. So you have 2 words before your word and 2 words after your word, and you're trying to predict the word in the middle. In this case, you've got one weight matrix for each of the words, trying all together to create some hidden representation that's just doing a sum and a linear activation, and then going out and predicting the one hot vector for your output layer. In the middle, these are the actual word embeddings, but we're going to talk about those in a bit. So those are the 2 models that the Word2Vec paper introduced. And the second thing that he introduced was, the author introduced, was a training methodology. So you could do things like this. Like, this wasn't necessarily, I mean, this was novel to an extent, but it wasn't like the big thing. The big thing was being able to do this fast. Because when you're dealing with, let's say, a vocabulary size of 400,000 or 1 million or something like that, doing this kind of an operation takes just a stupid amount of time. So the author came up with a number of ways to try and speed up this process. The main thing that's going on here on the output is you're doing a softmax over your vocabulary size. And like I said, if your vocabulary size is 400,000 or 1 million, doing that softmax is really computationally heavy because you've got to iterate over all the outputs for every individual output when you're doing your softmax. So there are 2 things you can do. One is a hierarchical softmax, which is we'll call it a statistical approximation of an actual softmax. So it's a lot cheaper to do than your actual softmax. You can get some speed up because you don't actually have to look at the individual output. You can generate some, you can generate a distribution and then draw from that distribution in a way that you expect your output, your softmax, to look like. And then the other one is, as opposed to doing a softmax, you can do what's called negative sampling. But basically, as opposed to needing to do the softmax, you can just sample the noise, or excuse me, sample the loss from a distribution, treat the loss as if it were coming from the categorical loss, and then backprop based on that noise. So there's a little bit of inaccuracy coming along there, but it's a big speed up again because you're basically able to skip the whole softmax step. Yeah.
I'm confused about this idea. What's the difference between this and the embedding we used in the homework?
What do you mean? Which embeddings did you use in the homework?
Just a linear.
This is the way to train that embedding layer. But like, if you made this, you would use the same thing used in the homework.
Yeah. So the structure in terms of code and stuff like that. I mean, this is just defining a model just to get at the embeddings. You can train your embeddings jointly if you want. Is that what you're asking?
So this is just training the embedding layer.
Correct.
It will not like associate with the loss function of the like iOS 10 cross into this loss function.
So I mean, you can use, you can put an embedding layer and then initialize the values in the embedding layer randomly, let's say, and then do a bunch of training and allow backprop to happen on that embedding layer. You can do that and train those embeddings jointly. This is just to pre-train these embeddings because a lot of times you have a lot of when you're training embeddings, you're able to draw from any type of corpus you want as long as there's some contextual structure. So you can draw from, let's say, the Google News corpus, which has X many, million tokens and million sentences, but maybe your data set only has 100,000 examples. So you're able to get word vectors or embedding vectors that are a lot more representative, we'll say, than those that you'd be able to train just on your data alone.
So what's the loss function for this training procedure?
So for negative sampling, it's a little bit weird. The math is described in the paper, but in general, it's just categorical cross entropy over your vocabulary. So one hot groups of one hot vectors in, different weight matrix for each one, going into a single layer of variable size, depending on however you want to define it, and then going out into a one hot vector for your over your vocabulary, or which the network's approximation of that one hot, and then you do categorical cross entropy back.
Like given context, one hot
given not there, so there's no time step notation or idea here. Just given the context of a word, given the words that are surrounding a specific word, predict the word that the words are surrounding, at least in the case of the SIBO one. And then in the case of the skipgram model, given a single word, predict the words that are most likely to appear in its context.
So the similarity is measured by what?
In terms of, what do you mean similarity?
It has some near vector, right?
So I'll get to that in a second, but that's in a couple slides. Okay. So that's where, so this is the structure for how the word vectors are actually constructed. So here we have the two models. You know, we take the context of the word and then we predict the word itself, or given the word, predict its context, depending on whichever model you want to implement. And then, you know, you train that for a while. Then you, at the end, you lob off the layer that's actually doing the prediction, and then you just use this hidden state as your word vector. This is super cool because you're able to, you know, just train it, do it with backprop, and then you know, having vectors that are near to each other is kind of a more of a property that we've just noticed occurs in these hidden layers. You know, you can imagine it as a sort of a simple motivation or understanding as to why this occurs is because, you know, similar words are projected close to each other in vector space, and so therefore you'd be able to use those predictions, you use that vector space to then predict that original word. So there's some kind of a motivation mentally for it, but it's kind of just something that we've noticed as as just a behavior of these networks. So yeah, so there are a couple of things to remember about WordDevec. The reason why it's stuck is because it provides a really fast way of doing this training, and it provided two models which were sort of novel that could get at this problem. Originally, when people were doing word vectors like these, it took a lot of, you know, hand tuning of the co-occurrence matrix to actually get vectors that looked like they could be near to each other in vector space based on their meaning or something like that. But this just does it using machine learning and gets it from point A to point B without having to do much. So it is an iterative model. It's based on backprop and stochastic gradient descent. So there are potentially multiple minima and multiple places for the model to get stuck when you're training WordDevec vectors. What the model is implicitly doing is doing a matrix factorization of the co-occurrence matrix, which we're going to talk a little bit more about with Glove. But they're doing that matrix factorization is a lot more computationally intensive than just doing backprop. So the main reason why WordDevec was a thing and continues to be a thing is because it's simple as far as the model goes, and so people can usually wrap their heads around it pretty easily. And it made this problem really tractable because you're sort of doing matrix factorization in a statistical way as opposed to a mathematical way. So then a couple of other cool things that people have noticed. These word vectors align across languages as long as the content of the training data is consistent. So if you train on parallel data for translations, so you've got one corpus in English and you've got another corpus in Spanish, then the word vectors are going to fairly closely line up in your vector space. So you know, the word vector for dog is going to be fairly close to the word vector for horse in Spanish or something like that. That's another one of those kind of, you know, inherent properties that people have been able to pull out, which is interesting. Again, there's some internal motivation based on the original reason as to why this works. But yeah, one of those interesting things. The other thing is that, you know, the meanings in this representation space are fairly consistent, and you can do vector transformations on top of them. So the vectors, you know, the vector that's needed to transform, let's say, Portugal to Lisbon is fairly close to the vector that's needed to transform Spain to Madrid. And so you can do some pretty neat matrix, vector math on top of these to, you know, do some logical things. This is kind of, this This was kind of noticed after the matrix math, doing man plus, or man, whatever, man minus queen, or no, man, that's it, man, that's it, yeah. King minus man plus woman equals queen. But this is kind of a visual motivation for it. And the other thing to note is that these are just PCAs over your high dimensional space. So there is some representation loss, but this is kind of just a general perspective on what's going on under the hood. So a couple of other extensions. You're not just limited to words. You're only really limited to what you can define as your context. So as long as you have something and then some sort of representation of what types of things that co-occur around it or are used with it, then you can create these embedding vectors for it. So a couple of different use cases that I've seen are Twitter users generating vectors for user accounts based on who that person retweets. Documents, hyperlinks between documents are another way of generating these vectors. And then I've seen academic paper authors, generating embeddings for authors based on who the author publishes with or something like that. So there are a bunch of different ways. You're not limited to words. You can extend it to anything you want as long as there's a definition of a context, and you can find a way of defining that context in a one-hot manner. But yeah. So a couple problems with WordDevec. The model is only trained on one-hot vectors, and it's trained using SGD typically. So it doesn't really have any idea of how often words co-occur with each other. It just knows that there's this example, which I've looked at, in which word A co-occurs with word B. And so there's not really a way to take advantage of that repetition. SGD kind of does it implicitly, but there's not really an explicit way of using it to keep track in this model. So that's kind of what Glove tries to solve. So Glove operates on the co-occurrence matrix. And the co-occurrence matrix is a matrix that's vocabulary size cross vocabulary size. And the number of times that the word co-occurs with each other is counted in each cell. So in this case, this is ratios, but it's the same idea. So Dave co-occurs with Bob 33% of the time, and so on and so forth. So that's the main idea behind Glove, is you construct this co-occurrence matrix. And you do a bunch of smoothing techniques and sort of math techniques to try and get the data nice and clean, and then you actually do that matrix factorization. So you try to take co-occurrence counts into consideration, does a ton of math to perform dimensionality reduction, and yeah, this is in general a count-based method, where the other one is a predictive method, where you're trying to learn that representation. So these vectors are constructed in kind of 4-ish steps. I'm skipping over a lot to present this one, but the idea is you construct the co-occurrence matrix, you calculate ratios between the co-occurrence counts and some words. So the idea is that kind of we'll call it a cube, where like you've got a co-occurrence count between, let's say, the word ice and water. And then you want to calculate the ratio of the probability of, let's say, steam and water and steam and ice. And that ratio becomes a new value. And then you kind of drop that into the cube, and that works as kind of a representative value of how often words appear in context. And then you do a bunch of smoothing and log normalizing on top of those things, or excuse me, normalizing and then log smoothing, and then you just do the matrix factorization to get the vector, to get the actual vectors out. This is a much more of a math-heavy implementation. It's not really a clean machine learning, just train the model and everything comes out. But the nice thing about it is that there's a much better motivation for it in terms of actually doing the matrix factorization. It's a computationally heavy thing, but it's something you can do to actually get at the data. So drawbacks for it, it takes a lot longer to construct, because doing a matrix factorization operation over your vocabulary, or over a matrix of vocabulary cross vocabulary, is a huge operation. But you only have to do it once. Once you have it, you've got your data, and you don't need to, model fine tuning or anything. It's just there. And the other thing is you can't really train these things in combination with with your neural network. These things have to be pre-trained and then used at training time. You could use them to initialize, but it's kind of a hand-wavy thing. So methods that are actually used in practice. So you can take pre-trained embeddings. Let's say you've generated a pre-trained embedding for all of your words using Word2Vec or something, Glove, and then you fix those vectors, and then you train your model using those vectors. That's totally fine. You can do that. There are a bunch of kind of different arguments as to which embedding type is better for your task. Sometimes Glove really is amazing. Other times Word2Vec is fantastic. But you can't really know ahead of time.
So just imagining, would Glove work better in instances where you have words that co-occur a lot of times, whereas Word2Vec doesn't take into account the counts?
Yeah, so there's some of the authors for Glove think that Glove is the future, and authors for Word2Vec think that Word2Vec is the future. But some examples where Glove clearly outperforms Word2Vec is on analogy tasks. So you can imagine that Word2Vec kind of has a little bit more noise in terms of the actual analogies because co-occurrence counts are skewed. So if you have a clear one like man, king, woman, queen, where there's a lot of information about how that's used, it's easy for Word2Vec and Glove to pull that out. But Glove, because it's actually doing the matrix factorization, if the data is really sparse, Word2Vec might lose that during SGD, but Glove will actually pull it out. So Glove you can think of as being good when data is rare, for words which data is rare, whereas Word2Vec is stronger, or not necessarily stronger, but certainly faster and easier to train. But yeah, it kind of depends on your use case. So the other way you can do it is you can generate some Glove embeddings or some Word2Vec embeddings, use those as seed values for your embeddings layer, and then train that embeddings layer jointly with your model. And that's totally valid. You can use them as an initialization. Sometimes your vocabulary is different than the vocabulary that's actually used in the word embedding space, or the distributions might be different. You might have training data that is exclusively talking about lawnmower repair, and so that data is going to have a very skewed vocabulary distribution, and so the word embeddings that are generated from Word2Vec or from Glove may have, if you're generating on different data, may have a different distribution. The word vectors might be skewed in one different direction, where it wouldn't do as well on your task. So training them jointly might make a lot of sense. And then the other way to do it is just train an embedding layer from scratch with your model. You can kind of think of doing this as doing Word2Vec in concert with your task. There are more parameters, so more chance for overfitting, more chance for error. Generally, having fixed word embeddings makes your model tend to generalize a little bit better. But if you have enough data to try and pull that out, then there's no reason why you wouldn't be able to do this. Okay, so then with that said, how are these things actually implemented in PyTorch, and what are some cool things that you can do with this? So let's say that we have two-dimensional word embeddings for these 5 words. So we've just got the quick brown fox jumps, and the column represents the word vector for these values, for these words. So first thing you're going to do is you're going to generate some IDs for it, which makes sense because the computer deals with numbers, not strings. And then let's say that we want to get the embedding for ID number 2, so which corresponds to the word brown. So the first thing we're going to do is we're going to, we have ID 2, or we have the word fox. We know the ID for it, and so we generate a vector where the value at number 2 is the number 1, and you just do matrix multiplication, and you're able to pull that out. So that's how everything's happening under the hood. Is there any confusion about this? Because this is kind of a key point.
I'm sorry, where are the 0.2 and 0.7?
Yeah, so you've got 0, 1, or excuse me, 0, 0, 1, 0, 0, right? So 1 is in your middle vector. Doing a matrix multiply with this pulls out this column and multiplies it by 1. So this 2 and 7 is that 2 and 7. So it's literally just a matrix multiply. Any confusion? because there are some super cool things that we can do with this, but if you don't get this part, then it's kind of.
What's the tables meaning? The top table?
Oh, top table is this guy. So we've got the quick brown fox jumps, and then this is the word vector for the quick brown as a column. Does that make sense? They don't have to add up. They could be whatever you want. Yeah, you know, this could be all zeros or it could be whatever.
Why there is two row?
So this is so you've got, let's take the word the as an example. The has two values in its embedding space, 0.1 and 0.5. We give it ID 0, and then we just replace that data. And then to pull out the data, you do a matrix multiply where your ID for the column that you want is a 1 vector. And then you do matrix multiply and you're able to pull out that column. All right. So there are a bunch of other cool things that you can do with this. So this is a traditional, this is the way that just a PyTorch embeddings layer works. You have some dense matrix of embeddings, and whenever you want to pull out a value from that embedding, you just pass the ID. This you do by yourself. You pass the ID. It generates the vector for you that's going to be used to pull out the embedding, and then it just does the matrix multiply. Yeah, and there are a couple of ways that you can optimize this. Obviously, you don't want to be doing a matrix multiply for everything, but if you want to do a matrix multiply for everything, there are some very cool things you can do.